In this video, we're going to start Lab 8 and cover the first section on point estimates, and then we'll continue in the second section on confidence intervals. So for this lab, you will need to download both the lab and an image file, which contains a central theorem that we're going to be using in this development. So at the start of this lab, I want to say we're making a pretty important turn in the course of this class from looking at just calculating probabilities in different situations or studying distributions. Now we're going to use these ideas to make inferences about some data that we've collected that is maybe representative of a population. It's a sample of a population. We want to start saying, how does this data, or to what extent can we say that this data describes a larger population? A very important question in statistics. So for this, we're going to be constructing and interpreting what are called confidence intervals. So the first idea we need to develop a little more is the idea of a point estimate, which is nothing new. We've talked about population means, population proportions. These are all sample means and sample proportions. These are all examples of point estimates. So we have the sample from which we're pulling data from a population. That's the paradigm, the framework that we're considering. And we're looking at this sample. So a point estimate comes from the sample. A population parameter comes from the population, and usually we don't know it. But in the case of developing some tools for making inferences, we're going to make this assumption that we know the population. And based off like a population parameter being a certain value, we can gather evidence for whether this statements we're making are true, or we have evidence that they are false. Okay, so the example we're going to look at is a proportion of adults in America that support the expansion of solar energy. And so we have a proportion of people, we're assuming we know it to be 88%. Okay, and we're going to simulate this. We could use 250 million like the textbook, but it kind of slows your computer down to have that much data. You could do it, but I'm going to make a smaller population of 250,000. So this population we can construct from the ground up if n, this is just an arrow is the same thing as an equal sign. I copied this from our textbook. So if you run this, this creates a population of 88% say support, 12% not. So if you run a sample of this population that we just constructed, like this is a lot of data. Don't run this. Don't type population and run it. If you run that, it'll print a lot of stuff, and it might slow your computer down. So in this case, we're going to just sample 10 people from it, and here's a sample of what is in population. We have people that say support and people that don't. Okay, so we got our population and we got a sample of the population. Remember that distinction? Because now we're going to start sampling from our population 1,000 entries. So we're going to use that same code. And without replacement means we can't sample the same person twice. That makes sense. We're going to run a survey and collect ratings on something like whether people support solar energy. We could collect 1,000 people. We're not going to collect data from all 250 million people, but we could run a sample of 1,000 people and use that to calculate the proportion of people that support solar energy. If you look at sample, well, it's just a lot of data. That's not really interesting. But I could say, how many of people in my sample equal support? If I do this double equal sign, that's a fancy way of saying which entries of this variable are support. And so it gives me true for the people that support it. And if I add up if I say sum of this, it adds up all the true, not the false. So this tells me 891 people support expansion of solar energy from my sample that I just simulated. And if we want to know the proportion, we just divide by 1,000. So this is the sample proportion. And we call this p hat, not fat, but p hat, and it's 891. How does that compare to the app? You might have different data because of your random generation, but based off your results, how does that compare to the theoretical population proportion? So this is called the margin of error. If we take 0.88 minus 0.91, and I make an R chunk for that, that gives us the margin of error. So the margin of error, I could have switched the order of this to make it positive. Margin of error is 0.011. That's how much my sample proportion was from the population proportion. Okay, so this is lays the groundwork for what we're going to do talking about a distribution of sample proportions. What if we repeat this process many, many times and want to know what is the sample distribution of these proportions that I drew? If I run this code, this code and this code, say 1,000 times, I can make a histogram of the different proportions we get, and that's exactly what you see here. This is some code I've made to run a simulation, and notice it takes a little bit of time to run because we're doing a simulation of 1,000 people 1,000 times. It's a fair amount of data, but even our computers, even a desktop computer, can do this quite easily. And so this tells me, well, look, of all the different proportions, most of them were centered around 88. And oh yeah, so this simulation I ran also gave me insert a code chunk here if it lets me. P hat is all the different values that I simulated, all the different sample proportions. So the first one said 0.886 proportion of the people were in favor of solar energy. The next one said 0.864. Do this 1,000 times. Well, what's the mean of that? That's kind of useful. And that's actually what we're asking on question 4. Sorry, I put that out of place. And what's the standard deviation of all those? So if I want to run those and have them both there kind of before me, this tells me the mean was basically 0.88, and the standard deviation was 0.01 of all these simulations. And if you want to get even closer to these values, let's kick up the number of iterations or the number of times we sample. If we sample instead of 1,000, 10,000, you can run this. Note it takes some time because we're doing it something 10,000 times. It involves sampling quite a bit of data. So you might want to delete this code if you don't want to burden your computer or to save time. But notice what happens. The distribution gets even more smooth and more like a normal distribution. So this is actually an illustration of what's called the central limit theorem, which says the more observations you observe, and if your sample size is large enough, the sample proportion will tend to follow a normal distribution, which is what we saw here, and the mean will be the actual population mean. The mean of all your samples is the actual population mean, and the standard deviation, this is called the standard error, which is the standard deviation of your proportions, follows this formula. So the only thing that we got to know about this is we do have to have a large sample size, and so there's some conditions that are considered sufficient for having a large enough sample size that are based off the sample size n and the proportion of your population. So we have to have some conditions. Let's get rid of that. That's not supposed to be there. We should have NP are greater than equal to 10 and n times 1 minus p have to be greater than equal to 10. So these are just some baseline conditions that we have to make sure. Then the theory holds. The other thing you should know is the observation should be independent. So these two conditions are related to the sample size being large enough, and these conditions are related to how we're sampling our data. So let's check. Let's see if our simulated data of 1,000 samples meets these conditions. And we'll assume independence holds. So firstly, we could say 0.88 times 1,000, p times n should be greater than 10. Oh, good, it is. And then 1,000 times 1 minus 0.88 should be greater than 10. And oh, good, it is. So we can verify that, yes, we can use the central limit theorem. Now, based off that, what is our p hat? What is the mean and the standard error of p hat? So the mean of our sample will be 0.88, and the standard error will be the square root. You can use this formula, SQRT, to make the square root, and then we have to put parentheses, and we do p times 1 minus p, and make sure that all is on the top of a fraction divided by n. So p is 0.88 and n is 1,000. We already found the mean. We know what the mean is. Okay, so if you run this, you get the standard error. Let's try running it again. Oh, and I have to put multiplication here. R doesn't know what I'm doing unless I put the multiple sign there. Okay, so now we can find out what the standard error is. And notice 0.01 is basically what we got when we found the standard deviation of all of our proportions. So where am I here? I think we're about done. So we're just verifying these conditions for the central limit theorem, and we'll want to do this in order to make good inferences. We have to know that we are satisfying the assumptions. Okay. So based on what this theory is all saying, the purpose of this theorem is to say that our sample distributions are normally distributed with mean 0.88 and standard deviation 0.01 approximately. Okay? And that tells us, now what we do, we know what proportion of values fall within a range. What if we want to know what values fall between 87 and 89%? That's what we're asking here. Well, since we know it's distributed normal, we can find out, this is actually saying, what's the probability? Okay, this is the same thing as saying, what's the probability that we're looking between 87 and 0.89 for our variable that's distributed normal? Mean 0.88 and standard deviation 0.01. So 2 weeks ago, we do the same thing. We use pnorm to find this, and we're looking at the distance between 8, 9 and 8, 7. And so now we just got to put what the mean is, 0.88, and the standard deviation is 0.01. Yeah. And then we're looking at the difference, because we're looking at the difference between two lower tail probabilities. And so we get about 68%. So all this theory tells us, okay, if I want to know my margin of error for a sample proportion like this, 68% of my data falls within this range. Okay, and so the last question for this portion is for you to do the same thing, but find the 2% margin, what percentage of the population falls within 2%. Okay, thanks for sticking with me. We'll see you in the next video or in class.